Okay, we want to do another example here for a type 2 foundation. We are going to find the settlement beneath the center and corner of this structure that is 60 feet by 60 feet, and we've got one center column, 4 edge columns, and 4 corner columns. And the soil profile, here's our soil profile. We have a layer of gravel, clay underneath it, layer of sand, layer of clay. And what we're going to do is we want to find out, so here's the structure. We're putting in a basement that's 6 feet deep. Our water table is there. We are going to put these piles in here like this at 12 feet, and here we have the piles going down to the top of the sand. So now the tips are in the sand. So what does that mean? That means that these are end-bearing piles. If the tips were in clay or silt, then they would be friction piles, but these are end-bearing piles. So the pile cap is 16 feet in width, and we are going to draw a pressure bulb from the pile tips there, and we know that, using 2B, it's going to take us down to from 25 feet plus 2 times B, which is 32 feet. 25 plus 32 takes us to 57 feet to the bottom of the pressure bulb. And we've done this calculation. So we have the top of the clay at 34 feet. We have the bottom of the pressure bulb at 57 feet. We add those two numbers together, divide by 2. We get 45.5 feet. That's the depth to the point of interest. And our H is going to be the 57 minus the 34 is 23 feet. So there's our point of interest at 45.5 feet. And we're going to stick with that point of interest. Now we also have this 6-foot basement, and so we are going to draw this pressure bulb and that pressure bulb is 2B, where B is 60 feet, so it's 120 feet, and this is 6 feet, so 6 plus 120 feet, I haven't quite shown it, but it goes just slightly below the rock here to 126 feet. But no matter, we are going to keep our point of interest. We keep our point of interest there. Why? Because the major portion of the compression of the soil is taking place in this region here, in this little region that is being stressed by all of these small pile groups. So our point of interest is going to remain is at 45.5 feet, and we need to investigate the effect of both the load due to the column and the effect of having the basement at that point. So okay, so the soil properties are given here. And of course, what we've done, and the whole purpose of of putting in these piles down to the sand layer is to avoid this clay. We're not going to load that clay. We are going to, and that's the purpose of it, because that clay may be soft, and so we're avoiding that top clay layer, and then we're only loading this bottom clay layer. This sand layer helps us. We can put our foundation in that little sand layer. Maybe, we don't know. We have to do the calculations. So, all right. That gets us started. Again, here are our soil properties. Know these: gamma D, gamma saturated, C epsilon R, C epsilon C, and the OCR for those clay layers. And we've done this before in the sense that we have 4 corner columns, we have 4 edge columns, and 1 center column. And that comes out to be the equivalent of 16 corner columns. The structure weight is 18 million pounds divided by the 16 corner columns. That tells us that the corner column load is 1.1 million. And that means that the edge is twice that, 2.2 million approximately. And the center column is approximately 4 times that, which is 4.4 million approximately. So that is for the column loads. Now, for the basement, what do? We figure out the volume of the basement. We're removing the gravel, take the density of the gravel. And so the volume of the basement, it's 6. The width of the structure is 60, so 60 squared. The depth of the basement is 6. 60 squared times 6 is the volume. And the unit weight is 110. So we are removing 2.3 million pounds of gravel. So we're going to, again, we break the foundation into the piles, center and corner. We're only asking for center and corner for this one, and the basement. And so we put down, our point of interest depth is the same for all of these. And so my center, 4.5 million, corner, 1.1 million. And then now when we do the basement, we're taking the whole basement load, that's of course negative, but it's 2.376 million. The area, now what are the areas then? Of course, the areas for the columns are the area of the pile caps for the columns, which is 16 squared, 256, whereas for the basement it's 60 squared, 3,600. So we take our Q, which is P over A, just divide those out, and we put in a negative sign for this one. And of course, yeah, this Q is going to work with, we're going to work with that Q for the pressure bulb, with the pressure bulb factor. So we need to get our pressure bulb factor. How do we get it? Well, we need to get our Z to our point of interest. Our point of interest depth is 45.5. The pile tips are at 25. So we get our Z of 20.5 for the piles, whereas the basement, we're taking the 45.5 minus the basement depth, which is 6. So the Z is 39.5 for the basement. And then we use our different B's at 16 feet for the piles, 60 feet for the basement. And we just do Z over B. And since we're doing now here's where, notice, we do our Z over B, and we go on our pressure bulb diagram below the center for the reasons that we described previously. But when we do the basement, because the basement is the whole building, we have to do our our little, to do the corner, we do our little trick, which is our z over b, we divide it by 2. And then when we get our pressure bulb factor, so here's our pressure bulb factor, we get our pressure bulb factor below the center on the pressure bulb chart, and then we divide it by 4. So here my z over b is 1.28, and let's see, do I have that now? On this one, we could see the 1.28 would take us, 1.28 is in here somewhere, so it's between 0.2 and 0.3. And so we got 0.23 for the pressure bulb factor for that one. And then the other one, we're at 0.658 and 0.658 over 2. So let's do that one. So 0.658 in here between 0.5 and 0.6, and then 0.658 over 2 is 0.33 approximately. So that's going to be in here. So it's going to be between 0.8 and 0.9, but then we have to divide by 4. That's our trick again to get the corner. So so we get 0.5, oops. So we get 0.55 for that one and 0.86 over 4. We take this pressure bulb factor, so these pressure bulb factors, we multiply it times our Q from the previous page, and so notice that our Q for the center column is different from the Q for the corner column. Whereas when we do our basement, so this is these two are the same. So
I didn't get.
Okay, so we get our delta sigma v's here, and notice I use the negative sign because those are going to be negative. We're removing the soil to create the basement. So here is our sigma prime I. I guess I didn't do that previously. That's the sigma prime before the building is built. So at our point of interest, you can pause the video. You should all be able to do that before the structure is there. That gives us our sigma prime I at our point of interest depth. It's 3250. And our sigma prime P is going to be the OCR times that sigma prime I. And so we get that our delta sigma V for our center column is going to be what? Well, it's going to be the column load, minus the basement. Column load minus the basement. There's my delta sigma V for the center. For the corner, it's going to be the column load minus the basement. Column load minus the basement. Get 868. So that's our delta sigma V. Our sigma prime I, we just calculated, is 3250. So, and our OCR of 1.1, I take that multiplied by, so I multiply those two. I got my sigma prime P. And then to get my sigma prime F, it's going to be my sigma prime I plus my delta sigma V gives me my sigma prime F. And so we can plot these. We have our, remember how we do this, we put on our sigma prime P at the inflection point there, and Our sigma prime I is less than that, so it goes to the left. Our sigma prime F is greater than that, so it goes to the right. That tells us we're going to use both parts of the equation. Looks like that. So for both of these, and we've done this many times, so there's our C epsilon R, the first part, C epsilon C, second part, and we get our epsilon V's for the center and the corner. We computed our H, which was 23 feet for both of them, and so we've got our center, corner, epsilon V, our H, multiply those out, we get a delta H, pretty big. And here is our footprint, and we use the Pythagorean theorem to get the L from the center to the corner. And there's the Pythagorean theorem there. We get our differential settlement divided by the L is 0.064, which comes out to be 1 over 15.7, which is greater than 1 over 300, so it's no good. This foundation doesn't work. You know, lots of things can be done here. You may have to recommend to your client to put in more columns because this doesn't work. You may need more columns. That's one alternative. You preload the site, put in possibly deeper basement. You just have to, all these options are available to you to redo this until you get the settlement correct. Good enough. In other words, get the settlement small enough so that we keep the rho over L to be less than 1 over 300. So all right, with this example here, we've done part of it already. Determine the equivalent number of corner columns. We've done that. Previously we came up with this being 64 corner columns, and the weight of our structure is 5 million pounds, so that we get a corner load of 5 million divided by 64, so 78,000 pounds, and then the edge is going to be twice the corner for 156,000. And the center is 4 times the corner, gives us 312,000. And then we want to get our Q. Well, our Q is going to be, in this case, it's 8. In other words, our pile cap is 8 by 8, so by coincidence gives us the number 64. But the reason we have the number 64 is that is the width of the pile cap. So don't mistake it for this 64. It's not that 64. So we get our Q, 64 square feet. I should read 60 to make sure that there is no confusion with this. This is 64 square feet, and that gives us the pounds per square foot for our Q here. So let's put that in there. And so we have the, that is our Q for our problem here. All right, so if we look at this, then, and we're going to find the point of interest, the H, and the delta sigma V for the center edge in the corner, then what we find is that for this soil profile, we have sand and silt, and in this case, we just have footings. We have footings under under our columns, we don't have any piles. So what do? We take our pressure bulb, we get the, which is 2B, so it's going to be 16 feet. 2 times 8, 16. And so it's 16 feet plus the 5 feet, takes us down to a depth of 21 feet. So this should read 21 feet. And so our point of interest is going to be the bottom of the pressure bulb. So the depth of the point of interest is going to be the 21 plus 8 over 2, which is 14.5 feet, and our H is going to be the 21 minus 8, which is 13 feet. And so we get our, like I say, the point of interest depth is 14.5. Then what is our Z? Our Z is going to be what? Well, we get our Z from the 14.5 minus 5. Where's that 5 come from? Is that. So that's going to be 9.5. So that's how we got the 9.5 for the Z. And we know the width we've given is 8 feet, so B is 8. And so we just find Z over B. We go in and we get our pressure bulb factor, so 1.19. And we can look at over here. So we go down 1.19, right about there. So we get between 0.2 and 0.3. And that gives us our pressure bulb factor of 0.27. And then I just multiply that pressure bulb factor times the Q that we got previously, times these Q's, and we get our delta sigma V. So we have found everything we need, and then the rest of the problem becomes the basic settlement problem. We found our sigma prime I. You can figure it out again with no structure being there. You can all look this over and get this value. You can all get that at our point of interest. And okay.